Hello, everybody. My name is Tan Çağatayacar. I am a teaching assistant of the course EE 446, which is Computer Architecture 2. And today we will look at the Vivado software. Right now I'm using 2024.2 version, but this is because I use this software also in another project. But we actually told you to download 2024.1 because this is the same version that the lab computers have. And if this doesn't match, there might be some problems, so we don't recommend you using another version. Now, today we will learn how to do pin assignments and how to create a project from startup, from ground up, and also how to generate Bitstream, how to synthesize your code, generate Bitstream, and upload your HDL design to the FPGA. Right now, I have the FPGA that we will use in the labs, which is Nexus A7 100T model. This FPGA is different from the FPGAs that you use in the Digital Electronics Laboratory, which was Altera DE1 SoC, if I remember correctly. Now, there are some different things about this process, about this FPGA board. First of all, instead of 8 switches, now we have 16 switches, which gives us more control, which is also always good. We have 16 LEDs. We have 8 7-segment displays instead of 6, which is great. And we have 5 buttons instead of 4. So we also have 2 more RGB LEDs, but I don't think we will use them in this course, in the laboratory sessions. And we need to know how to assign them in order to be able to interact with our design and with the processors that you will design in this course. So first we need to create a project. So what we will do is here when we open Vivado, this is the screen that you should see. And from Quick Start, you can select Create Project, and from Create Project, you will create it with a wizard. You can press Next, and then you will select a project name. For this, I will say, today in the tutorial we will do 7-segment display. So I will say 7-segment as my project name. I will specify project location, and I will select create project subdirectory. This is because this is my parent directory that I keep all of my projects, and under this directory I want a separate project folder dedicated for this project files. I will select next, and then I need to select my project type. Most of the time, and throughout this semester, you would want to select RTL project. You can unselect this to specify sources at this time. This is because in your lab sessions, what you will do is in preliminary, you will design all of your Verilog files in preliminary and test them with CocoTB software, test bench. And after that, in lab, you will create an RTL project and you will import your sources. And if you unselect this, you can import your source files, your Verilog files at the beginning, or you can just unselect them and create or sort your files later on. So right now I don't have any Verilog files ready for me to source, so I will not. I will select this, so I will not specify any other source files. Others you can check, but we will not use them. Now we need to select our board. So up here you will select boards first. You might need to press this refresh button. Let's search our board. If our board is this, if this doesn't comes up, just press refresh. It will do this. You will wait a bit. You need an internet connection for this step also. Let's wait until this finishes, then we will continue. I wish I hadn't pressed this. but it's okay. Most likely you will need to press it. I had to press it also. If you see a download button, press it and it will download the board and necessary source files that it needs. And after that you can click on this and it will direct you to a reference page from the manufacturer of this board. This will come in handy later on, so keep this open. Okay, once you select this, you can choose next. You will see the board parameters here that you selected. You can press finish. And after you do that, you are greeted with the project manager, as you see. And here, as you can see, we don't have any source files in our project. Now, what we will do is we usually will do our simulations outside Vivado with separate software with CocoTV. So we will not be using simulation sources and utility sources, but we will create our design sources and we will use constraint files to do pin assignments. So this design sources is the HDL files, the Verilog files, the VHDLs, the system Verilog files that you will create or source to define your HDL design. And these constraint files are the ones that allow you to do pin assignments. Aside that, you can also give some time constraints, but this is out of the scope of this course. So these are that. This folder doesn't contain anything, and sources folder doesn't contain anything. First thing I want to do is I want to add a top module. So here you can select what do you want to, what kind of a source file you want to add. We want to add a design source. Here we will create a file. Also you can do it from here, and we will create a Verilog file, and I will name this top as our top module. You can name it differently, it doesn't have to be top. You can specify your input and output buses already from here, but we will skip this and I will press yes. So because you can specify them later on, and we are used to that in digital lab. Now I can see my file is created under this folder, and here if I double click on it, it will open up here. And if you see these three little square boxes and with one green at the top, this symbol means that this is automatically recognized and set as the top module. This file is set as the top module. And later on, when you have multiple source files, you will see that only your top module has this symbol on it. And if it doesn't, you need to right click, and there should be as this is disabled right now, but normally if it's not a top module, this will be enabled. You need to press this to set your top module as the top module. Right now we have an OM2 module. I will raise these so that it's not cluttered. In here I need to define my input and output wires or registers or whatever, and I need to define my HDL designs. Now, as you can see, as you remember, at top module, what we do is we only have pins that are connected to the board, and we do all the wire assignments inside. So now we need to know what pins that we will use on the board. For that, if you remember the reference that we opened, here you can check reference manual, but it will probably be a very big PDF file. But basically, you can see what you will interact with, and what we are looking for here under the documentation section. We are looking for the master XDC files. So all of the constraint files here in Vivado have the extension .xdc. So master XDC file is the file that contains all of the assignments ready for a specific board. So every board has a master XDC file already available by the manufacturer. If I click on it, it will direct me to a GitHub page, and you can see all of the different boards available, and we need to find our board for the master XDC file. Here, this is our board, and I just want to download this one. But I already downloaded it, so it added this one here. As you can see, these are the same files, so I will just delete this. This can be deleted too. Yes. Now, yes, this file. Now I want this file in my project. So what I want to do is I want to actually add sources, and I want to add constraint. So this needs to be selected. I will press next. Here I will select add files, and here from I will go to my downloads folder. It's already there. I will select my XDC file that I just downloaded. I will press OK and make sure this is checked, and this will copy my selected file under my project folder, which is needed if you are going to upload your project to the Auto class, so that your folder that you uploaded contains every source file that you are using in the project. Press finish, and now you will see your XDC file here. As you can see, you have a lot of ports here, a lot of peripherals, a lot of ways to interact on the board that are already been configured for you, and they are all commented. And you need to uncomment the ones that you will use. And let's say you want to use a clock, then you will uncomment this, and there you have it. You have a 100 megahertz clock. Let's say we want to use the switches. Then what you do is you uncomment these parts. We might want to use LEDs. Let's uncomment these as well. And today we are doing a 7-segment tutorial, so I will need these pins as well. I could also use buttons, but I mean, it will be probably overkill for now. These are enough. Okay, so here you can see a bunch of things, so I will go over them very easily. This grade clock is only valid for clock, and for other pins it's not there. And this is for time constraints, and it helps Vivado when you synthesize your design. It helps Vivado to satisfy Fmax, the maximum frequency conditions, and checks that it can satisfy those constraints. So this is helpful, but it's out of the scope. You can just use it. And for each port that you will use, each pin that you want to assign, you use this set property directive, and then you specify in a dictionary manner package pin. This pin corresponds to this chip's pinlet. So in that package, J15 corresponds to a pin that is on the chip, and this IO standard specifies that we will be using CMOS in output and 3.3 volts level. And you can also specify 1.8 volts or different voltage levels. There are some options, but we will only use 3.3 for now. And I don't recommend you changing these levels, as they are selected to be compatible with the board. Then here you select which input pin this package pin will be connected to. As you can see, we have a switch bus, and each of these bus bits are connected to a switch. So here, if I save my XDC file, here what I should do is, if I want to get these switch values as my input to my top module, I need to write here input, and these are wires, and I have 16 switches, so I need to create a 16-bit bus, and their name is SW. And that's how I connected these switches to my top module. Now I will do the same thing for the clock. If I copy this, what I will write is here input wire, since this is not a bus, it will just be this. And I will connect my LEDs, and these will be outputs. So, and I will make them registers for now, because I can feel I feel like I will use them as the registers. And 7-segment display, all outputs. And here you will see that we only have how many? 8 here, 8 here. We only have 16 pins for controlling 8 7-segment displays. And you might think that this is not enough, as if you remember, we had 7 pins per 7-segment display. So at the digital lab, the FPGA we used had 6 7-segment displays and 7 pins for each, resulting in a 42 pin count. But here we only have 16 pins that will control more 7-segment displays, 8 to be exact. So it's not trivial. It will not be the same as just setting 7 pins for each 7-segment displays and then controlling them. We need to do something different, and we will explore that. Now I need to specify all of them. And also, you can change these names, by the way, but I prefer not changing them. So what I need to do is I need to specify output register. First, I will do the bus, which is AN. AN is short for anode, by the way, since these are all LEDs, and it's an 8-bit bus. AN and not N. And I will have no, these are not buses. CACB up to CG, and we have DP. I need to write this. So CA, CB, CC, CE, CB, CF, CG, and we have DP for decimal point. And here, just like that, we connected our top module with the pins on board. Now I need to create another module that will control one 7-segment display. So let's do it. That's how we did in the digital lab. So what we will do is, now I want to create a new source file. I need to press the plus, and I will create a design source. Next, I will create a new file, which is a Verilog file, and I will name it SSD for 7-segment display. I will press now OK, and I will not specify any input outputs right now. And it created my module. As you can see, it doesn't have this top module symbol, and it's all okay. Now, 7-segment display, if you remember, what do we input to this module and output? We input a 4-bit value, because with 7-segment display we can represent a hexadecimal digit, and a hexadecimal digit can represent 16 values, which corresponds to 4 bits of information. So we will specify an input wire, and this will be a 4-bit value, and that 4-bit value name should be, I will select this value. And we have an out, we will need an output. An output will be registered, because I will design it that way. And do we want to control the decimal point? We don't want to. We didn't in the digital lab. So I will only have 16 values here as my display. If you remember, this is the exact same input and output module that we had in the digital lab. Now, the way I do it, I don't remember if it's the same, is I create an always block, and in the sensitivity list I just make a combination of, I do begin and end, and here I open a case 4 different values. Now here I have 16 possible values for the value, and I need to write for each one of them. If I want to display 0, I want display bits to be equal to some 7-bit value. And how am I going to determine the values of each display control bits? I need to check which of these control pins are mapped to each LEDs on 7-segment display. And for that, I can always consult the internet. I can just say, as you can see, I searched it before. I will write my board name and 7-segment. Let's see what comes up. I usually go to images right away. And you can see we have a great from the manufacturer's site. That's always good. And you can see here it says for the top it's A, B, C, D, E, F, G, and we have the DP for the dot. And you can see these are the same namings that we have here, CA, CB, CC, and this C at the in front of these signal names means it's the cathode side of the LED, and these ANs, these AN pins corresponds to the common anode of the LED side that's connected to each digit. So AN0 is corresponding to the first digit, AN1 is second, AN2 is third digit. And right now I'm only interested in controlling one digit, so I will use the AN0. That means that I need to set this to some value as well. Now, this is also will be helpful because it shows me the circuit. These are not direct connected, but these are driving some sort. And as you can see, this is there is an inverter here for driving. If you remember if you have taken digital electronics course, you will immediately see that this is an inverter gate, because this only works, this transistor only conducts when this is low and not high, because there needs to be current. So we can just say that these are these pins, the anode pins here. These anode pins are inverted. So in order to activate them, we need to supply 0, and we don't want to activate them, we need to supply 1 to them. So for the AN0 that we want, if we supply 1 here, the voltage will be the same for these two sides. And if no current is passing from the emitter pin to the base, there will be no current passing here. And if no current passes here, if I supply 1 here, this will, all of the LEDs will be on, no matter my cathode signals. So when I supply 0 here, as you can see, there will be voltage difference here from emitter to base. And since a small amount of current flows here, a large amount of current can flow here. And depending on our cathode signals, we can control our display. So when we supply 0 here, we need to supply 1 to other ones so that these are not open. And then what I want is, I need to, if there is 1 volt, if there is voltage here, if I want to LED to emit light, I need to set ground here. So if I want, these are also in a sense inverted. So if I want here A to emit light, I need to set CA to 0 and others to 1. If I only want A to emit light. So all of these signals are inverted. And if I want this first digit A to light up, I need to set these wires to 0 and everything else to 1. So with that out of the way, Now we can continue programming our 7-segment display module. So the display doesn't have the individual CA, CB, CC signals. We can either define it in the top module, or I can split them here. What should I do? I prefer doing it like this. Since we will use this here anyway, what I can do is this. I can input my value from the first 4 switches. These are connected to value port of my 7-segment module, and the display will be the concatenation of these signals, not including the decimal point. And if I just do it like this, what happens is, if you remember from digital electronics, it's hard to remember, but I know digital electronics laboratory, our display, the hex signal that's connected to the FPGA in the older boards, the buses, display buses, first bit, the least significant 0th bit, is connected to this. But right now, we are connected the CA signal to the most significant bit side, to the display bus. And if I want the same signals, the same structure as the old code, I need to reverse these ones. So I'm going to do that for my ease. F, we want E, this is the C, B, and A. And that's the reason why I switched the order here. And now I have 2 options. I can either do all of these assignments by myself, manually, one by one, like for 0, which one of them will light up and which one of them will not. But I can also use the SSD module from Digital Electronics Laboratory. But I will go from the hard path, and I will do it, but I will speed up the video so that you guys don't suffer. Or you can just skip this part, and I don't need to speed up. Okay, this is better. You can just skip to the font if you are not interested in how to do it, because we have already done it in laboratory. Now, since these signals will be inverted, what I would like to do is I would like to specify which one of them I want to, which one of the LEDs that I want them to lit up as 1s and the others as 0, and then I like to invert them so that these signals are correct. Now, if I want A to lit up, I need to specify the first bit as 1. And if I want, since we will be doing 0, only G will not be lighted up. So G is the last one here. So all of them will be 1. And here we have 7 digits. Okay, that's correct. Now I will do the same thing for 1, except only B and C will be lighted up. So this will be 0, and the others will be 0. Now we will do the same for the 2. And for 2, it will be like this. So C and F will not be lighted up. And this will be like this. Yep. Let's do 3. And only F and E will not be lighted up. And these are E and F, I believe. Yes. Now for 4, we will do this. A, E, and D will not light up. So A, E, D is this, and F will be lighted up. 5. For 5, we will do this. So B and E will not light up. B, and E. For 6, only B will not light up. It goes to there. For 7, ABC will light up. So the first 3 signals only will light up. Other will be 0. And I forgot to change this to reset. Yes. I will fast direct this now. 8, all of them will be lighted up. And for 9, E will not light up. Nice. For 10 and 11, you remember this is A. How do we do A? We do it like this, so D will not light up. And D is the middle one here, yes. And yes, this is 10. 11 is B, and B is like this, right? No, B is this. This is B. Okay, B. A and B will not light up, so the first 2 will be zeros and the others will be ones. Okay. 12 is C, and C is done as big. We can also do it little, but big is better. So A, F, E, A, D, E, F. Yes. This will be 0. Sorry. A. Where did it go? Okay. A. No, D, E, F. Okay. And 13, 14, 15. Now 13 is D. D will be like this. So F and A will not. We will light it up. And yes. No, yeah. Okay. I did wrong. Yes. This is D. And E. E will be. How do you write E? This is no. This is 3. This is E. Okay. So BC will not light up. Did I do 3? I don't remember. Okay. This is E. So BC will not light up. Okay. I just need to do this. 3 is correct. Okay. And F. F will be like this. No, F will be like this. So B, C, D are not lighted up. B, C, D. Okay. I hope these are correct. So now we have our assignments here. And on the top module, we have connected our display. And if you remember, we needed to only activate the first 7-segment display. So what I will do is I will assign. What did I do here? I will assign and as this. If you remember, it was inverted. So what I will do is I will just invert here. And I will only activate the first digit. Now, what I will also do is I will convert these to wires, and I would want the LEDs to light up when the switches beneath them. These LEDs are right on top of switches, and when the corresponding switch is lighted up, I want the LED to light up as well. The switches are turned on, not lighted up. Okay, this should be correct. So let's see if we did a correct job. So the way we synthesize our code is there are like 3 steps to it until you can generate a programmable file, the so-called Bitstream file that you will have at the end and upload to the FPGA. So wait, I need to do something here. Okay, so we have a problem here. Say should not be using output port connection. These should be wire, not registers, because we are just connecting them to from a module. And these displays are registers. Okay, now it should be correct. It would be better if I erased these things. Okay, so again, first, when you want to generate a bitstream to be able to program the hardware, what the compiler does is it first runs synthesis, which generates the design as the logic gates. Then it runs the implementation. You can do them manually as well. And then when you run the implementation, it converts that logic design to a physical design that can run on your FPGA. And lastly, you can generate a bitstream which converts that physical design into a specific configuration file that your FPGA expects, and we will then open the hardware manager and then upload it. But when you click to generate bitstream, it sees that the design is not up to date, and it runs synthesis and implementation and then generate bitstream automatically from startup. And you can watch the process from here. First synthesis will run, then implementation will run, and when the implementation finishes, it will here say writing bitstream. If we have done a correct job, let's see. By the way, this is the demo code that runs when you just connect the FPGA to your computer when it's powered up. So this is not the code that I uploaded. It's interesting, right? We have 8 control signals for anodes and 8 for cathode, but it can light all of them at the same time. So there's a trick there. We need to do something different in order to be able to control them at the same time and display values at the same time. It will not be as same as the thing that we did in the digital lab. And that's why I actually imported clock here. We will see. This process, depending on the computer, will take some time. And since I'm also recording, and there are like 3 video sources in the recording, I think it takes longer than usual. And now you can see the right bitstream is complete. This means that we can open our hardware manager now. We will allow everything that it asks us. And then we will say open target, and we will connect auto connect. Make sure your FPGA is connected before you click on the auto connect. It should automatically detect and open the device. And what you can do is just press here program device. Make sure the name matches with your top module, the top bit, and you will press program. And as you can see, we have R0, and only the first digit is displaying. And if I switch it to 1, as you can see, the LED on top of the switch lights up because of the assignment, and then our value is 1. Let's try 2. Nice. 3, and then 4, 5, 6, 7, 8, 9, 10 is A, B, C, D, E, F, and we have all of the cases here. Now we make sure that we can do the same thing as what we did in the digital lab, but this is not enough for displaying for all of the digits at the same time. And for that, what we can do is we can select all of these 1, right? And That way, we would technically light up all of the 7-segment displays, but then we limit ourselves to only displaying one hexadecimal value, but on each digit. Let me show you what I mean. I can just close the hardware manager, and then I will change these to all ones, and then save, and then I will generate Bitstream again. And this is the process that you will do when you are constantly trying and experimenting with your code. One great thing about Coco TV is that when you are not dealing with physical input output, and even if you are when you are dealing with these, it's so fast, so much faster than this process. That's why we are promoting and like forcing you to use those kinds of simulation software. Let's wait. And the thing that we need to somehow exploit the fact that we can turn on and off each digit and like display different things on each digit, but not just at the same time. But one power of FPGA is we can do it really fast, and we can take advantage of the human eye because our eyes cannot process the visuals not that fast. So the idea is called multiplexing. What I mean by multiplexing is that what we will do is we will control each digit and we will display different things on each digit on this FPGA, but not at the same time, but at a sequence. And we will switch the content of each digit at the different time steps. And if we do it really fast, our eyes will not be able to see the flickering, and we will be able to display different values for each digit at the end. Now, our bitstream is completed. I can just select open target from here as well and auto connect. And here, since we are connected, I can just program the device program. And now we will see that all of the LEDs light up. So we can light LEDs at the same time, but all of them have to show the same thing. And this is not acceptable for us. So we now need to implement the idea of multiplexing. And for that, we need different time steps, different behavior on different times. So that's why I included clock here. So let's close the hardware manager. We are back to our project manager. Now we need to use this clock, and I need an input here for that. Or this can stay the same. What I will do is I will use something like this. Now my SSD converts the values to the each signals that we have. Now what I will do is I will create another module that will use the SSD. Let's see. I will create a design source. I will create a file, and this file name now will be SSD multi-SSD. Let's say MSSD multi-SSD. Right? Okay. I will finish. I will not specify input output now, and as you can see, I have my file here. And as you can see, SSD is not sitting under the top module. This is because we are using the SSD module under the top module, and it kind of associates the hierarchy, detects the hierarchy, and then shows it like this. It's like a neat feature. Now, instead of using this directly here, I will use this under here. And I will not change my SSD here. We already know what this does. And here I will still have display. Actually, it would be better if I copy these. Yes. I will still have the same display output, which will be fired because I'm just connecting it to the SSD module. This will be directly connected to here, but with 8 segment displays, I can display 8 hexadecimal digits, which each hexadecimal digit can display 4 bits. So 8 times 4, we can now display a 32-bit value. Therefore, our multi-SSD, multi-7 segment display module can display a 32-bit value, which I will select as this. Now, this value we need to somehow index this and only show a 4-bit value here. So if I wanted to show the lower 4 bits value with my 7 segment display, then I could have just done this, but what I need to do is I need to slide this 4-bit window on different time steps. So my multi SSD module needs a clock signal, and that clock will be connected. Can do this, that, and we can do this. Now we will connect this to here. The value, we have 16 bits coming from the switches, but our value needs to be 32-bit because we can display 32-bit. What I can do is concatenate a known 16-bit value on the upper side. So what I can do is this. I can always display a, let's say, ABCD here. Or I can display EE, computer design, here, like this. Yeah, that's even nicer. Okay, and I can also, display the switch values on the lower 16 bits, lower 4 digits. So here, this side will display the switches values, and this side will always display EECD, according to what I aim. Now, we also need to connect the display. I wish I hadn't erased this. What I can do is to, okay, it's easier to write. Did I do it? Oh, right, okay. Ctrl X. Yes, I need to do it like this. No, that's not it. Fire, that's correct. This should be this. Value is 32 bits now, and I did it like this, and these were not placed this. Now we have been. So if we now compile this and generate Bitstream and then upload it, it will have the same behavior, and it will only show the first 4 digits, and it will not do anything for the upper parts, because this is essentially the same code, same design. What we should do is now, according to our clock signal, while clock, we should switch this value, and the way we can do it is we will need to have an always block, and this always block will always execute at the positive edge of our block. Yep. Then at positive edge of our clock, we need to slide this 4-bit window. And the way we can do it is we can define a register, and we have 8 digits, right? So I want to indicate the index of this display is this digit. So this index should be 3 bits for indicating an 8 value integer. And what I want to do is, I want to increment this index so that we always slide our index. So 0, then at the next clock cycle it will be 1, it will be 2, it will be 3, 4, 5, 6, 7. And then since this index register is 8 bits, 3 bits, it will overflow and it will automatically return to 0. So 0, 1, 2, 3, 4, 7, 5, 6, 7, and then 0. It always slides. So that's how I generate that action. And the value that the 4-bit value that I will select needs to also slide. So how I can do is I can do it like this, times 4. Actually, this only since this will not be like this, and I can do this plus id x times 4. Now, rightfully so, the Verilog module will give me an error here, or at least it's supposed to give me an error here. But this effectively satisfies what I want, but this is not accepted in Verilog because that the 4-bit bit should not change in order to be able to be synthesizable. But here at the starting bit index and the ending bit index, I have a variable, and Verilog does not like variables when you are showing a range here. So the only way to implement this, there is a special way of showing it, and we can just look at here. Verilog variable. I didn't variable indexing. Let's search that. Yes, variable. You will need to use indexed part select operator. This is called this, and how it's done is you only specify the starting bit, the least significant bit that you want to start from, and you write, instead of a semicolon, you only double column, you write plus double column, which indicates that starting from this bit, I want this many bits. You can also do it in the reverse direction, but it's not pretty. So what we need to do is that we need to specify it as this. Whichever digit we are showing, the least significant bit will be given by idx times 4, and we will take the next 4 bits after that. And now Verilog is happy. The reason that I am doing times 4 is that I want to slide by 4 for each digit, because each digit is 4 bits value. Now I can test my code. Let's generate Bitstream. Now, to be honest with you, I don't expect this to work. And the reason you suspect is that I haven't done anything wrong with the code. And the idea is right. The multiplexing idea works. It's used in many ways. Whenever you see a LED matrix, there's probably multiplexing. And the code that I wrote is also correct. But remember we had here, I can show here. Remember that here there are some resistors and then transistors here. These effectively introduce additional output impedance to these ports, which increases the maximum frequency that they can operate. So here there is, since this increases the R times C, there's always capacitance in these kinds of circuits. So these resistors increase the RC capacitance, which in turn increases the time period of these connections. And I cannot switch these ports at 100 megahertz, which is a very, very high frequency. So we will see what happens when we do it, but the solution is rather easy. We will just need to divide this frequency, and we already know how to do it. But I wanted to show you that what happens when we do it really fast. So we have forgotten to switch the anodes at the correct time. So I need to also implement that. And the way we implement it is that we define the anodes as output here. I can maybe do it as wire. It's an 8-bit bus, and its name can stay AN. I need a comma here. I also need to define it here as dot AN, and it will be straightly connected to the AN. If I can write. Yes. So now I will not just assign a value to AN, but I need to switch the anodes, and I only want to turn one of them at a time step. The way I can do it is I can just assign, and I can remember we need to invert it at the end. I can just shift this 1 bit to the digit index that we want to display, and then invert it so that our signal is correct. And this will only activate the digit that we want to display. Now let's try this one. And our design is now completed. Now we will open target, auto connect. Let's see what happens. Program device. Yep. And as you can see, there's like faint. It's not clear. And if I do the one you can see a little bit here, but it gets fainter as it goes because our circuit cannot switch fast enough. And if I select all of these digits to 1, like the first 4 of them, these, you can see 1, but it's not. There are still faints of others because we have other digits ECD that the module wants to display, but it cannot switch these ports at these high frequencies. Now, the only way we can fix this issue is to reduce our clock. And to see actually what our program does, I will reduce this to 1 Hertz so that you will see what the program does. So, and I will also do this inside the module, and I will where should I do it? Here, the way I divide the clock is I usually make a 32-bit register called count. I always start it at 0, and then I do I increment that at the postage of our clock. Plus 1, and if this count reaches the value that I want to divide the clock to, let's say 10,000 for now, I reset the count. It will be 0. And if we haven't reached this count, and then we will increment count. And I also only do the thing that I want to do when we overflow the count here. So if I want a 1 Hz signal, then I need to divide this 100 megahertz clock to 100 million. So here now I have 100,000. Now I have 100 million here, which is enough because 32 bits can hold like up to 4 billion. So 100 million is in the scope. Let's see what our module does at each clock cycle. Okay, this is completed. Now we can open our target. It's connecting, and then we can upload our code. See. Program device, okay. And now we will see. There you go. D, C, E, E. It's correct. And if I change some values here, 1, 8, C. Nice. As you can see, our digits show the corresponding values that's inputted to our module, but now this is too slow. Now we need to find a sweet spot, and that it's a wide range, but usually the eye cannot see on, like, if you exceed 100 Hertz, it's okay. And so what I usually do is I set it at 1 kilohertz, which is not too high, but it's not noticeable. And it seems to work to jump down. So let's try it with 1 kilohertz now. Generate Bitstream. It's not up to date. Sometimes the Vivado does it, and I'm glad that it's now doing it, because I've changed the MSSD module now. Yes, it's 100 now, but if I write something other than that, it's not updating. If I Control S, save. Yes, but now here at the top left, it should show that the design is out of date because I've changed the design, and it shouldn't give me this. Whenever this happens, I usually, I don't know if there is another way easier than this. I just close the project. We making sure that I save my files, then reopen the project. Now I open my files and check they are the same, and now you can see synthesis and implementation out of date. And if I press the generate bitstream, now it should generate the bitstream correctly. PB. And the generate bitstream is completed. We connect to the FPGA now, and then program the device. And now you can see all of the values at the same time, the EECD that we have. specified, and the values that we can set with the switches. Like this. And that's pretty much it. The MSSD and SSD module will be supplied to you because you haven't seen multiplexing in digital design, and we don't expect you to do this on your own. It will be supplied, and this module will be used when you design your processor. This module will be used to show some register values and other stuff that, and like program counter or jump registers or stuff like that. So they will come in handy, and I hope that you learned how to use Vivado and how to import other source files as well as create new ones, and how to do pin assignments. And if you have any more questions regarding to this and problems, we first encourage you to try this on your own in the lab when you have access, and use the lab computers for sure for at least once, because those are the computers that you are forced to use in the lab sessions. So make sure that you are comfortable with the software before the lab sessions start. Thank you for watching, and I think this is a rather long video, but the content is also a bit heavy. Thank you for listening.